Okay, so this is the midterm review for EGME 410, spring 2021 for midterm 2. Okay, so I looked at the poll on Canvas, right before this, and it looks like the topics that people want to see for the review, and it was a tie. It was a tie for first, were approximate solutions to weak form problems and also finite element form problems. Okay, and so those will be the two topics that I want to focus on most for this review. Okay. And the order is good because going over the weak form first, I think will lead us into the finite element form solutions. Okay, so my plan for this review is, for each of the topics, I'm going to talk just a little bit about the theory behind it, kind of the general approach that you would use to solve these problems, and then do one example each, and then those are going to come from the recent homework that was just turned in. Okay. All right, so let's get started. All right, so the first thing we're going to go over is the weak form solutions. Right. And so, I can see why there might be some confusion about, how to actually formulate these weak form solutions based on, kind of what's in the lecture notes. But because I think, I think the first time I went over the derivation in the lecture notes, I think I did kind of a specific case where the Neumann boundary condition or the natural boundary condition was strictly on one side of the domain. Okay. And so I want to do a case where I want to give you kind of the general form of these equations first, and then we'll do kind of a case, an example from the homework. Okay. And so the most general form for the weak form solutions is given by the following equation. Okay. And so we're going to take the integral from 0 to L. And then in the integrand, we're going to have dw dx, which is the derivative of our weighting function. Okay. Then we have our material constants. And so first we have, and so this is for heat transfer at first, okay? And so for heat transfer, we have the thermal conductivity times the cross-sectional area, okay? Okay. Then we have the derivative of our solution function dt dx, dx, okay? All right, and so that's on one side of the equal sign. And so on the other side, we have all of the forcing terms, okay? So first we have integral from 0 to L of our weighting function, w of x, okay, times our source function, s of x, okay, dx, plus, then we have our natural boundary term, or our Neumann condition term, okay. And so we have w times, let's go with q bar, okay, so that's going to be our heat flux, times area, okay. And this is going to be evaluated at the location of our Neumann boundary. Okay. Right. But in particular, I think probably the easier form to do this is just to have this evaluated from 0 to L. Okay, because remember those are the bounds of our domain. Okay, and usually, what's the case, or actually always what's the case, is that we're only going to evaluate this last term here at a single location of our boundary. Okay, but that's going to be where the natural boundary. So depending on if the natural boundary or the Neumann boundary is on the left side of the domain at x is equal to 0, or on the right side of the domain at x is equal to L, that's going to change how we evaluate this this term. Okay. All right. And then let's talk about our requirements. And so the requirements are for all w of x with w at the essential boundary, or wherever our Dirichlet boundary conditions are, is equal to 0. Okay. And then we have to supply the initial or the Dirichlet boundary condition to our solution as well. Okay. All right. And so here, w gamma u right here, this is the location of our Dirichlet boundary. Okay. And so that's basically whenever we have like a temperature supplied, or maybe like a displacement supplied, like a fixed support. Okay. And so remember, at those locations, we have to require both the weighting function as well as the solution function. Well, we have to require the weighting function go to 0 there, and then the solution function has to match whatever the Dirichlet solution is there. Okay. All right. And so this is the form of the weak form for heat transfer. Okay. And so, I know some people have gotten confused about, applying this for heat transfer versus for elasticity. Okay. And so, I want you guys to kind of, not worry about that because they're mathematically, they're exactly the same thing. Okay. And so you're going to have the exact same equation here. It's just some of the symbols might be a little bit different. Okay. And so if we were doing this equation for elasticity, we might have, instead of the thermal conductivity here, we'll have the Young's modulus. Okay. And of course, instead of temperature, since you don't solve for temperature and elasticity, what you have instead is the displacement, which we use the symbol U for that. Right? Also, instead of a thermal generation function, we have a body force function. Okay, so that's usually given the symbol B of x. Okay, and instead of a heat flux, what we have instead is a traction boundary condition. Okay. But mathematically, they're exactly the same. And so, I don't make any distinction between them. And neither should you. And so, when you come across a weak form solution, kind of just extract just the kind of underlying mathematical problem, and then work with that instead of getting caught up on, is this heat transfer? Is this, elasticity? And so the only thing you have to really worry about between heat transfer and elasticity is just making sure you plug in the right values for stuff. Okay. In terms of like the symbols and the names or everything. Okay. Okay. All right. And so basically, the way that we go about solving this is we solve it, assuming an approximate form. Okay. And so this kind of methodology that we're using to first, first we assume a form of the function and then we kind of plug it all in. This is the kind of the exact same method that we use, when solving for, this is kind of the exact same way that element stiffness matrices are derived for the finite element form. Okay. And so normally what we do is we make two assumptions here. And so let's take kind of the elasticity case. Okay. And so we have to assume. Okay. We have to assume that our solution function U of x and our weighting function W of x, we have to assume that these take some kind of form. Okay, and so for instance, U of x here, usually we assume it to be some kind of polynomial function, and so something maybe like a linear function, a quadratic function. Okay, and so if you have a quadratic function, it might look something like this. Okay, where we have to include all of the terms up until the quadratic term. And so we have a0 plus a1x plus a2 x squared, okay? And then we have to assume the exact same functional form for w of x, okay? Albeit with different constants. Okay. And so if our u of x here is a quadratic function, then our w of x is also a quadratic function. Okay. And so, choosing the form of the solution is usually a, it's usually something that that you as the user will have to make, and that determines, the accuracy of your solution, all that stuff. But for the purpose of this exam, very similar to what you saw in the homework, I'm going to tell you, what order the function that you should use. Okay. Okay. And so let's kind of just walk through, the steps that you would have to do to start with these and then end up with the solution. Okay. All right, so let me go on the next page. And let me write out the functions again. And so the first step that you're going to do here, when you first come across an approximate weak form problem, is that you're going to apply the Dirichlet boundary conditions. And remember, so those are the boundary conditions where you set the solution have to equal to some part at some that we have a specified value for the solution at certain parts of our domain. Okay, and so let's say, for example, let me check to see if this is different than our example problem here. Okay, all right. So let's say, for example, that we have a fixed support. Right. a fixed support at x is equal to L. Or let me plug in a number for this. So let's say a fixed support at x is equal to 4, okay, 4 meters. And so to apply the Dirichlet boundary condition, all you would do is plug in x is equal to 4, okay? And so a0 plus a1 4 squared plus, a1 4, sorry, plus a2 4 squared, okay? And since this is a fixed support, this has to equal 0. And so we have a0 plus 4a1 plus 16a2, okay, is equal to 0. And then from this, we can solve for a0 here very easily. We can say that a0 is equal to minus 4a1 minus 16a2, okay? Right. And then now what we can do is that now that we have this expression for a0, we can take this and plug it back into our equation up there. Therefore, we can eliminate a0 from the equation. Okay. And so if we plug in back for a0, what we get is u of x is equal to a1 times x minus 4 plus a2 x squared minus 16. And so I just combined the a1 and a2 terms. Okay. And so in this formula that I have boxed down here, it's still, we still need quite a ways to go, but you can see that we've eliminated one of the constants, right? Because our goal here for the approximate weak form solutions is that we want to solve for all of these constants here, a0, a1, a2, such that we get our solution. Okay? And so the more that we solve for these constants and the more we can kind of plug in for them, the closer we are to our solution. Okay. And the general rule of thumb is that every time you plug in for a Dirichlet boundary condition, you should eliminate, or you should be able to solve for one of the constants. Okay. And then to solve for all the other constants, you have to plug that into the weak form. Okay? And so you should be careful for cases, like we saw in the homework, where you have more than one Dirichlet boundary condition, right? And so I'm talking about cases like 2a, 3a, things like that. Okay. And so when you have more than one Dirichlet boundary condition, you have to apply multiple of these and solve for multiple constants in order to solve for them. Okay. And so just be careful for those cases, because I got a lot of questions on that. Understandably, because we didn't do anything like that on the in the lectures. Okay. Okay, so let's do an example now that showcases this process. So let's do homework problem 3b. Okay, so this is homework 3, problem 3b. Okay, and so in this problem we have a tapered rod. And so all tapered means is that, it's the area is decreasing as a function of x, okay? Our left side of the rod right here is going to be at x is equal to 0. And then on the right side, we have x is equal to L, okay? All right, and on the right side, we have a known heat flux. And on the left side, we have a Dirichlet boundary condition of a fixed temperature of 100 degrees C. Okay. And then in the middle of this rod, we have some thermal generation, which we're calling S of x. Okay, and so let's go ahead and define some of these parameters. And so the length of this rod is going to be 2 meters. Okay. Thermal conductivity is going to be 15 watts per meters degrees C. Okay. Area, and so area is going to be changing because we have a tapered rod, right? And so our area is going to be 0.5 minus 0.1x, okay? And so that lets our rod decrease in area. And then our thermal generation function will be 1/2 x squared, okay? All right. And so for this problem, we want to solve for an approximate weak form solution. Okay. And then we're going to assume a linear form of the weighting and solution functions. Okay. And so a linear form basically only has two terms, and so it's going to be a0 plus a1x. Okay. And then w of 0 here is going to be b0 plus b1x. Okay. All right. Okay. And so let's go about solving this this guy using the method that we kind of talked about before. Right? So the first step is we're going to apply our Dirichlet boundary condition. Okay. Okay. And so our Dirichlet boundary condition says that our temperature at x is equal to 0 is going to be 100 degrees C. And just like we mentioned before, so when we apply this Dirichlet boundary condition, we'll be able to solve for one of the constants. Okay, and so let's go ahead and plug in for that. And so our t of x here is a0 plus a1 times x, where x here is 0. Okay, and so 0 times a1 is obviously 0. And so this tells us that a0 is equal to 100. Okay, so that's great. And now let's do the same thing for the weighting function, okay? But instead of setting the weighting function equal to 100 at x equals 0, what we're going to do is we're going to set it to 0, okay? Because remember, one of the requirements for the weighting function is that it disappears on our Dirichlet boundaries. Okay, and so we go ahead and plug in for that. We have b0 plus b1 times 0, okay? And so this tells us that b0 is equal to 0. Okay, and so that gives us two of these constants already. And so the only one that we have to solve for now is just a1. And the way we're going to solve for that is we're going to plug back into the weak form. So before we do that, let me go ahead and compute the derivatives here. Okay, and so first we have dt dx. And so dt dx is going to be just the derivative of our temperature function with respect to x. And so this gives us a1. Okay. Next, we have dw dx, which is the derivative of the weighting function with respect to x. And this just gives us b1. Okay. All right, and so now we're ready to start plugging into the weak form. Okay, so let me go ahead and pull it up on my screen again. Okay. And our weak form is given by integral from 0 to L dw dx times k times a dt dx, okay, times dx. Okay. And so this is equal to integral from 0 to L w of x s of x dx plus w q bar a evaluated at from 0 to L. Okay. Okay. And so right away, before we actually plug in anything, let's deal with this term first. Okay, because remember this term, what this represents is all the Neumann boundary conditions. which in reality are the heat flux boundary conditions. Okay. And so at this point, what we have to ask ourselves is what sections of our domain, or what part of our domain, do we have a heat flux boundary condition? And so to answer this question, let's look back at our domain picture, okay? And then we have to look at our two domains right here, our two boundaries, right? So we have our boundary here at x is equal to 0, and we have our boundary here at x is equal to L, okay? And so at x is equal to 0, we've already applied a boundary condition here, and this was a temperature boundary condition. Okay? And a temperature boundary condition is the same thing as a Dirichlet boundary condition. Okay. And on the right one, even though it says no heat flux, this is basically our Neumann boundary condition here. Okay? So because we're not specifying the temperature. All right, and so since we only have a Neumann boundary condition on the right side of the domain where we have our heat flux there, we can go ahead and ignore this quantity here at evaluated x is equal to 0. Okay. Because we can't evaluate this at x equals 0 because we don't have any heat flux there. Okay. All right, and so when we evaluate this at x is equal to L, what we have is W of L times Q bar, which is the amount of heat flux at that location, okay, times A of L. Okay. All right, and so what you do from here is you plug in all the values here for W and A. Okay. And so for W of x, remember our W of x is just simply B1x. Okay. But instead of x, we're going to plug in L. Okay, so B1 times L times our heat flux value. And so our heat flux value here is just 0, okay, because we're no heat flux. And then we have area evaluated at L, okay? And so our area evaluated at L is going to be our area function, which was 0.5 minus 0.1x, okay? So we have 0.5 minus 0.1 times L. And so from here, for a lot of cases, you would normally have something here that you would have to evaluate. You get something that's non-zero. But because we have this kind of special case where our heat flux is 0, we can go ahead and just kind of eliminate this entire term from the expression. Okay. And so, for this particular problem, there's no contribution from this. But remember, this is kind of a special case where we have no heat flux there. Okay. And so normally, this term will contribute something if the Q bar or T bar is non-zero. Okay. All right, but for this particular problem, it doesn't contribute anything because it's just 0. Okay. Okay, and so from here, we're just going to plug in for everything else. Okay. And let me do each of these kind of one at a time, and then we'll kind of, once we evaluate each of these integrals one at a time, we'll kind of pull it all together at the end. Okay. And so let's do the first integral here. So the first integral is integral from 0 to L dw dx times k times a dt dx. Okay. And so let's go ahead and plug in everything from here. Okay. And so first we have integral from 0 to L, and our L here is just 2, I believe, right? L is 2. Yes. So we have integral from 0 to 2. Okay. dw dx, which we've already computed, is b1. Okay. Our K value here is 15 watts per meter degrees C. Okay. Our area here is 0.5 minus 0.1 x. Okay. And our dt dx here is just an A1. Okay. And then we have that all multiplied by dx. Okay. All right, and so let's go ahead and simplify this integral here. And so I'm going to pull out all of the constants. And so we have a constant of b1, a constant of a1 times 15. Okay. Integral from 0 to L of 0.5 minus 0.1 x dx. Okay. Clean up this 5 a little bit. Okay. And now what we can do from here is we can integrate. Right. And so we integrate this. We have 15 b1 a1 times 0.5 x minus 0.05 x squared, okay, because we have to divide by 2 here. Okay. And then we're going to evaluate this from 0 to 2. Okay. All right, and so now we have 15 times b1 a1 times 0.5 times 0.2, or 0.5 times 2 minus 0.05 2 squared. Okay. And then we have the same thing evaluated at 0, but it's just all zeros. Okay. And so we have 1 minus 0.05 times 4 times 15. Okay. And so overall, this gives us 12 b1 a1. Okay. And so that's the first part of this problem. Okay. So that's the first integral. And so now let's go ahead and evaluate the second integral now, which is the integral from 0 to L of w of x s of x. Okay. All right, and so just like we did with the previous one, we're going to go ahead and plug in for everything. Okay. And so first we're going to plug in for L, and so L we know is 2, and so we have an integral from 0 to 2, okay, of w of x. And so w of x in this case is b1 times x, okay. And then our s of x here, we're going to plug in is 1/2 x squared. Okay, dx. All right. All right, and so let's go ahead and factor out the constants again. And so we have b1 divided by 2 integral from 0 to 2 of x cubed dx. Okay. And so this is a simple integral, so we can just simply integrate it. Okay, so b1 divided by 2 times x to the 4th divided by 4, evaluated from 0 to 2. Okay. And so we plug this in, we get 2 to the 4th power, which is 16. Okay. And so we have b1 divided by 8 times 16. Okay. And then we finally say that this is equal to 2b1. Okay. Okay. And so now that we solve for these two constants here, or these two integrals, let's go ahead and plug all of that stuff in. Okay. And so first we have this term right here, which is 12b1a1. Okay. So we plug back into the weak form. We have 12b1 a1 is equal to 2b1. Okay. And remember, we're writing this equation to solve for a1. Okay. Right. And we can see here that we have b1 on both sides, and so these guys can just easily cancel out. Okay. And what we get is 12a1 is equal to 2. Okay. We divide both sides by 12 and we get that A1 is equal to 1/6. All right, and so now that we have A1 and we have A0 that we solved for from the Dirichlet boundary conditions, we can plug all of this back in and get our final solution for T of x. Okay, so we have T of x is equal to, remember, A0 plus A1x. And so we plug in for these guys, we have A0, which is 100, plus A1 here, which is 1/6 times x. And that's how you get the solution for that problem. Okay. All right, and so I know there's quite a few steps here with the approximate solutions for weak forms, but each step by themselves are not too bad. So just kind of take it just kind of step by step, and you'll get a solution just like this. Okay, and so this is a good example problem to practice for the exam, because the exam problem is not too different from this. Okay. And so there is our weak form solutions. And so now let's go on to finite element forms. All right, so finite element forms is kind of the next step after the weak form solutions. And it's basically, how we can turn, a situation like what we just looked like, where we have like a governing differential equation, we convert it to a weak form, and then from that we derive a finite element form problem from that. Okay. Okay. All right. And so the starting point for this is our weak form. So let me go ahead and write that down again. Okay. And so our weak form here is integral from 0 to L dw dx times EA du dx is equal to integral from 0 to L w of x b of x dx plus our natural boundary term, which is w a t bar. Okay? And this is evaluated from 0 to L. Okay. And so, starting point here is the same, but, the difference here is that instead of doing this over the entire domain, which is what we did for, for the previous one, what we can do is we can solve kind of individual problems like this for each individual element of our domain. Okay. Okay. And so think of finite element form as kind of solving individual problems for each of the different elements. Okay. But just like all the finite element form problems that we that we talked about before, ultimately the goal is to take a situation like this and turn it into a linear equation problem. Okay. All right. And so if you just for kind of reminder here, our system of linear equations basically means we have a matrix of coefficients multiplied by a solution vector is equal to some right-hand side forcing vector. Okay. Okay. So in other words, we have a solution, we have a situation that looks like this. We have K. K is our, stiffness matrix of coefficients. Okay. F here is our right-hand side forcing vector. Right. And so this is going to contain things like the like any kind of body forcing term, right, or any kind of loads, that traditionally goes into this forcing vector. Okay? And then U here is our solution vector. Okay. Right. And so the solution vector is ultimately what we want to solve for. And so the way that we solve for this, just like the same way we did with trusses and beams, is we take our coefficient matrix, we invert it, and we multiply it by the right-hand side. Okay. And of course, this is something you don't want to read backwards. You can do that, but I can't because I'm being recorded here. Okay. And so the way that we go from integral expression up here, over to a linear system right here. I'm not going to go over the whole derivation again because that's in the notes. But basically, the way that we do this is we, I'll just kind of sum up the important steps. Is that we formulate, our solution vector and our solution function and our weighting function in terms of shape functions. Okay? And so, we'll probably have a situation where we have u of x is equal to u1 n1 of x plus u2 n2 of x, okay? And w of x is equal to w1 n1 of x plus w2 n2 of x, okay? Where the key component here is now these n functions, okay? And these are our shape functions, okay? And so in order to get the finite element forms, we're going to, first of all, take derivatives of these and then plug them into our, into our weak form, okay? And so just to kind of jog your memory, let me kind of write down the expressions for these shape functions because we're going to need them in our solutions, okay? And so most of the time for our, for the ones I'm going to ask you to do on the exam, I'm just going to give you a linear functions. And so for linear shape functions, they take the following form. So we have n1 of x. n1 of x is equal to a x2 minus x divided by x2 minus x1, okay? And then n2 of x is equal to x minus x1 divided by x2 minus x1. Okay. And I put it in this form because it might be slightly different than what we have in the notes, but I do it here because what we can do is we can define length of the element the length of a 1D element is just the difference in between the coordinates at the far side, which is x2 minus x1. Okay, and so L, I'm just going to use the symbol L here. L is going to be x2 minus x1. Okay, and so this lets us formulate the shape functions here. N1 of x is going to be equal to x2 minus x, all divided by L, and N2 of x is equal to x minus x1, all divided by L. Okay. All right. And so with these shape functions and, with the weak forms and, and you can take the derivatives of this, just fine. What you can do from here is you can kind of plug all of these guys in. Okay. Okay. Actually, let me compute our shape function derivatives here because I think that might be a little bit make things a bit more clear. Okay. Because we are going to need them in a bit. Okay. And so we take the derivative of this first shape function here with respect to x. And so what we get from that is a minus 1 over L. Okay. Okay. And we take the derivative of the second shape function with respect to x. And we have just 1 over L. Okay. All right. And so with these, now that we have the shape functions here, we are ready to write out the forms for the element stiffness matrix and element forcing vector. Okay. Okay, so let's start with the element stiffness matrix. Okay. You can't have a finite element solution without element stiffness matrices. Okay. Okay, and so we give this a symbol KE. Okay. And it's an integral expression. We integrate from x1, which is the coordinates of the first node of the element, to x2, which is the coordinates of the second node. Okay. Okay. Then we have this column vector dn1 dx, dn2 dx, okay, times the Young's modulus times the area times a row vector dx. Okay. Let me just go ahead and plug in for the shape function derivatives because we have it here. And the fact that they're constants means that we can just factor them out of the integral. Okay. And so we have integral from x1, x2 of negative 1 over L, 1 over L, okay, times EA times negative 1 over L, 1 over L, okay, dx. Okay. We can factor these guys out of the integral, and then we end up with a 2 by 2 matrix. Okay, so I'm going to multiply this matrix by this matrix, factor it out of the integral because it's just a constant. Okay. And so that gives us 1 over L squared minus 1 over L squared minus 1 over L squared, 1 over L squared. Okay. Integral from x1, x2 times E times A dx. Okay. And this right here is your element stiffness matrix. Okay. And so I took this, a couple steps further than what was in the lecture notes, just because, I'm giving you the shape function derivatives here, okay, and I'm telling you that they're constants. Okay. I can't take it any further than this because we have to account for the fact that the Young's modulus or the area might vary with space, okay, and so we might actually have to integrate them. But for the cases where those two are constants, then we can just pull them out of the integral and just multiply it by that. Okay. Okay, and so that's the element stiffness matrix. Now let's look at the element forcing vector. Okay. Okay. And so the element forcing vector. And this one, I can't do too much here to simplify it, but I can at least do something here. Okay. And so our element forcing vector is given by integral from x1 to x2 of column vector here, n1, n2, times our body forcing term, b of x, dx, okay, plus our, Neumann boundary condition. So we have n1, n2, okay, a, t bar, and this is evaluated at Neumann boundary. Okay. All right, so we can simplify this a little bit. We can plug in for n1, n2. And then what we get from this is 1 over L, because that's going to factor out of the whole thing, okay? Integral from x1, x2 of, remember n1 here is x2 minus x, right? Yes. Okay, we have x2 minus x, and then x minus x1, okay, times b of x dx, okay, plus x2 minus x minus x1 times a t bar, where this, we're going to plug in the value of x where we're at the Dirichlet boundary condition, or at the Neumann boundary condition. Okay. And so actually, you know, for your forcing for this kind of last term right here, there's kind of 3 options for this. Okay. Okay. And so the first option, which is going to be the most common, is that this is just going to be 0, 0. And this is for the case when our element does not border a Neumann boundary. Okay. Okay. And so that's going to be your most common case because, you know, a lot of times your elements aren't going to border those. Okay. Next, we have the case where this is just going to be 1, 0. Okay. And so in this case, this is for the case when the Neumann boundary condition is on the on x1 of our element. Okay. Okay. And then the last case here is, you know, is this going to be 0, 1? And this is when the Neumann boundary condition is at x2 of our element. Okay. So let me do this. Okay. Just to make sure that, you know, we can get 0, 0, 1, 0, and 0, 1 here, I'm going to put the L's back on the ends for that one. Okay. Okay. And so that was quite a lot of theory. And so let's go ahead and run through one of the one of the homework problems. And lo and behold, we're doing the exact same problem as what we did, you know, previously. Okay. And so we're going to do problem 3b, but with 3 finite elements. Okay. So this is problem 4b on the homework. We're going to repeat 3b, but with with 2 finite elements. Okay. This is good practice actually, because the exam will also only have 2 finite elements. Okay. And so, you know, it doesn't say in the problem, but basically what you can assume is that the 2 elements here are going to have the same same length. Okay. Okay. If the problem doesn't tell you how long each of the elements are, then you can assume that they're going to be equal length. Okay, so let me go ahead and draw the geometry one more time just to kind of remind ourselves. Okay. Right, and so we have a situation like this, okay, where we have no heat flux. Okay. The temperature here is 100 degrees C. Okay. We have a thermal generation term. This is 1/2 x squared. The length of this guy is 2 meters. Okay. The thermal conductivity is 15. Okay. And then the area function is 0.5 minus 0.1 x. Okay. All right, and so let's go ahead and start solving this this problem. Okay. And so, when you're doing these problems with finite elements, the first thing you're going to have to do is find the element stiffness matrix and element forcing vector for every element. Okay. And so let's go ahead and break this domain up into the two elements that that was mentioned. Okay. And so we'll call this element A. We'll call this element B. Okay. Okay. And then we're going to solve for the for the temperatures at each of the nodes. Okay. And so let's start with element A. Okay. And so the length of element A, which is going to be the same for the length of element B, is going to be just 1 meter. Okay. And then the thermal conductivity is going to be 15. Okay. Area function is going to be the same as up here, so this is 0.5 minus 0.1 x. Okay. And then most importantly, I think we need to set the bounds for this element, and the bounds are going to be x1 is going to be equal to 0, and then x2 here is going to be equal to 1. Okay. And so let's go ahead and plug into our equations from the previous page and solve for the element stiffness matrix. All right, so element stiffness matrix from before, this is equal to 1 over L squared minus 1 over L squared minus 1 over L squared, 1 over L squared, okay? Integral from x1, x2 of this element times k times a dx. All right, and so let's go ahead and plug in for K, A, and L. Okay. We plug in for L, we have 1 over 1 squared, which is just 1. Okay. So 1 minus 1 minus 1, 1. Okay. Plugging in for x1 and x2, we have integral from 0 to 1. Okay. Plug in K, we have 15. And then for A, we have 0.5 minus 0.1 x dx. Okay. All right, so let me go ahead and factor out the 15 from both from inside there. Okay. And then so we have I'm going to factor out the 15 and multiply it through, and so we have 15 minus 15 minus 15, 15. Okay. Right. And then we have integral of 0.5 times 0.1x, and so this is going to be 0.5x minus 0.05 x squared, okay, evaluated from 0 to 1, okay. And so we plug in for that. What we get is 15 minus 15 minus 15, 15, okay, times 0.5 minus 0.05 is 0.45. And so we perform this multiplication. What we get is 15 times 0.45. We get an element stiffness matrix of 6.75 minus 6.75 minus 6.75, 6.75. Okay. And so that's the element stiffness matrix for the first element. Now let's work on the element forcing vector. All right, and so the element forcing vector, we're going to use the same formula that we did before. Okay, and so the formula for that was Fe is equal to 1 over L times integral from x1, x2 of let's see, x2 minus x and x minus x1, okay, times, what was it, s of x in this case, okay, dx, okay, plus, sorry, brain fart, okay, so n1, n2 times a q bar. Okay, and so first let's go ahead and evaluate this guy on the right here, okay? And so for element 1 or element A, we're nowhere near the Neumann boundary. So, you know, node 1 and node 2 of this element, no heat flux boundary conditions, okay? Okay, and so since there's no heat flux boundary condition for this, we can just go ahead and just cancel that term straight away, okay? Okay, and then from here, let's go ahead and plug in for s of x, okay? And we can go ahead and plug in for L too, right? And so this is going to be 1 over 1, which is just 1, times integral from 0 to 1 of x2 minus x. x2 in this case is 1 minus x. And then x1 in this case is 0. And so we just have x right there, okay? And then our s of x here is 1/2 x squared, okay? And so let's go ahead and multiply this through and then perform the integration. And so let's pull the 1/2 out in front. Okay. Right. And so we have integral from 0 to 1 of x squared minus x cubed and x cubed here on the bottom. Okay. All right, and so we perform this integration, and what we get is x cubed over 3 minus x to the 4th over 4, and then x cubed, or x to the 4th over 4 down here. Okay, evaluate this from 0 to 1. And so we perform that math, and what we get is 1/2 times 1/3 minus 1/4, which from my calculator tells me that that's 1/12. Okay, and then on the bottom there we have a 1 to the 4th power over 4, and that's just 1/4. Okay. Right. Let me go ahead and multiply the 1/2 just to make kind of one nice number. So we multiply the 1/2 through, and what we get is 1 over 24, and then 1 over 8. Okay, and so that's the element stiffness matrix and element forcing vector for you know, that first element. Okay, right, and then from here we can go ahead and repeat that exact same process for you know, for element 2. All right, so for element 2, okay, element 2, you know, all the properties here are going to stay the same. The only difference here is that x1 and x2 are going to be different. And so for element 2, x1 is going to be equal to 1, and x2 is going to be equal to 2. Okay, but we can use the exact same calculations as we did before, right? And so we know that you know, we can go ahead and kind of pick it up from here, okay? Because the function for a and the function for k is still the same. Actually, let me just pick it up from here. It's probably the easiest thing, right? And so we know that ke for element 2, ke for element 2 is going to be 15 minus 15 minus 15, 15, okay, times 0.5 times x minus 0.05 x squared, okay? But now we're going to evaluate this from 1 to 2 instead of 0 to 1, okay? All right, and so let's go ahead and evaluate this guy, okay? And so we're going to first evaluate this at x is equal to 2, and so we have 0.5 times 2 minus 0.05, 2 squared, okay, minus 0.5 times 1 minus 0.05, 1 squared, okay? And so we punch all that into the calculator, we get 0.5 times 2 minus 0.05 times 4, okay, minus 0.5 minus 0.05, okay, and overall this gives us 0.35, okay. All right, and so KE here is going to be 0.35 times 15, and so this gives us 5.25 minus 5.25 minus 5.25, 5.25, okay. And so that's our element stiffness matrix for element 2. And now let's do the element forcing vector, okay, where I'm going to use just kind of the same result here. Okay, so I'm going to start just from right there. All right, so FE is going to be equal to 1/2. And let me go ahead and fill in for this. And so this is x cubed over 3 minus x to the 4th over 4. Okay. And on the bottom here, we have x cubed over 3. And we're going to evaluate this from 1 to 2. Okay. And so that's the term for the thermal generation. But we also have to add in our Neumann boundary condition term. Okay. Okay. And the reason we're doing this is because element 2 here borders one of the Neumann boundary conditions. Okay. Okay. And so what we're going to do here is we're going to do N1, N2 times Q bar A, okay? And so if we look back at our original domain, we can see here that, the heat flux boundary condition here is on the right side of the domain, okay? And so if we look at element B here, the node that borders the heat flux boundary condition is the rightmost one, or the one on the right. Okay. Okay. So node x2 of element B borders heat flux BC. Okay. And so since it's node x2 of our element, then what that tells us is that this N1, N2, here is going to be 0, 1. Okay. And so of course, and at this point, it doesn't really matter because our heat flux here is 0, and so the 0 is going to knock it all out. But I wanted to show you what you would do, in case there was a flux boundary condition, because I'd say that's something good to know for the exam. Okay. All right, and so let's evaluate the area function at x is equal to L, okay, or x is equal to x2. Okay. Okay. Remember, x2 in this case is 2. Okay. And so, our area function is 0.5 minus 0.1 x. Okay. And so this becomes 0.3. Okay. And so we plug in 0.3 there. Okay. Again, for this problem, we had a heat flux of 0, and so it doesn't really matter. But that's what you would do in case there was a heat flux there. Okay, so now let's go ahead and evaluate this integral term here. And so we have 1/2 times x cubed over 3 minus x to the 4th over 4. Okay, and so we're going to evaluate that at the integration bounds 2 and 1. Okay, and so first we're going to have 2 cubed divided by 3 minus 2 to the 4th divided by 4. Okay, minus 1 cubed over 3 minus 1 to the 4th divided by 4. Okay, and so that's going to be the top entry of our vector. And on the bottom entry, we have 2 cubed over 3 minus 1 cubed over 3. Okay, and so we evaluate that in our calculator. Let me go ahead and punch that in. And so we have 2 parentheses 2 cubed divided by 3 minus 2 raised 4 divided by 4, okay, minus 1/3 minus 1/4, okay. And so this is minus 17 over 2, okay. And on the bottom, we have 2 cubed divided by 3 minus 1/3, okay. And so this is 7 over 3. Okay. And so we multiply the 1/2 through. This is a minus 17 divided by 4 and a 7 divided by 6. Okay. Right. Remember, we got, in this case, we have no contribution from the Neumann BC because our Neumann BC is a 0 heat flux. But normally, you would have something there. Okay. Okay. And so now that we have the element stiffness matrix and the element forcing vector for all of the elements, we're ready to assemble this all together. Okay. Because remember, back from our truss and beam days, once you have the element stiffness matrices, you assemble all of them, you apply the boundary conditions, and you solve. Okay. All right. And so let's look at assembly. All right. And so for assembly, in this case, we're going to have a 3 by 3 matrix. Okay. Okay. And then we're going to fill in, the contributions from elements A and B in the exact same way that we did before. Okay. And so we're going to draw out kind of a box here for element A. Okay. So we have to do the contributions over here too. Okay. And then the contributions also from element B. Okay. All right, and so let's go ahead and fill in the values here because it's not that much. Okay. And so for element A, remember our element stiffness matrix was it 6.75? Okay. Okay, so we had 6.75 minus 6.75 minus 6.75. Okay. And we have 6.75 in there, but we're going to add that together with the contributions from element B. Okay. And so for element B, we had 5.25. Okay. And so for that spot that we're intersecting, we have 5.25 plus 6.75. And so that's going to give us 12. Okay. And then for this, we have minus 5.25, minus 5.25, 5.25. Okay. And then we're going to do the same thing on the right-hand side. And so for the right-hand side, we're going to have our forcing vectors here. Okay. And so for element A, we have 1 over 24 and 1 over 8. Okay. So we have 1 over 24. In this entry, we have a 1 over 8, but we're going to add that to the top entry from this one. So we have 1 over 8 minus 17 over 4. Okay. And that's going to be a minus 33 over 8. Okay. And then in the bottommost entry here, we have the last entry, which is 7 over 6. Okay. And then everything that's not filled in, remember, we can just fill in zeros for that. Okay. But we're not quite done yet because we still have to apply our Dirichlet boundary condition. Okay. And our Dirichlet boundary condition here was applied on node 1. And so we're going to erase this entire row, just like we always do. Okay. Put a 1 there on the diagonal. And then on the right here, normally what we do is we replace this with 0. But since, we're doing a thermal simulation, we have to make sure that our first node here matches that first Dirichlet boundary condition, which is 100. Okay. Okay. All right, and this is as far as I'd want you to take it for the exam. And so, for the exam, all you have to do is just put together, the element stiffness matrices and assemble them. But you don't have to solve for this because, normally this requires some MATLAB for you to do that. Okay. Okay, and so that concludes the review. I think that made really good time, and so that was about a little bit over an hour 10 minutes. Okay, and so hopefully this review was helpful for you guys to see the problems worked out like this, and you can expect the exam to look very similar to these problems. Okay, all right. So best of luck studying for everyone. If you have any questions about anything, remember, please don't hesitate to let me know, and I'll see you guys next week.